Let's get this show on the road. So we talked about matter, and matter is made up of atoms. And then we talked about atoms of different elements. Talked a lot about the periodic table. Atoms are awesome. We talked about electrons and the nuclei the electrons are associated with. And then we talked about compounds, different types of compounds, covalent compounds and ionic compounds. But compounds are basically atoms joined together in a repeating unit, whether it's a molecule or a formula unit. And now finally we're going to talk about chemical reactions again. Actually, clear back in Unit 1 we talked about chemical reactions. And we said sometimes you can tell a chemical reaction occurred and sometimes you maybe can't tell a chemical reaction occurred. But a chemical reaction gives you new substances. A reaction gives you new substances, a chemical reaction. So we're going to talk about that more. And the way, see, I'm not very good at English. I passed and all that, English Comp 1 and 2. I was looking at my transcript the other day. I think I got a C+ in Comp 2. Oh, my gosh. But one of the things about science and chemistry is they're more concise. It's more about numbers, and a chemical equation representing a chemical reaction is so concise. And so, like, I wish all life was like that. So we're going to talk about chemical equations that describe chemical reactions. So a chemical reaction is one that, like I said, new substances are formed. And you kind of see me kind of put out two hands. And we read a chemical reaction. We're going to use chemical equations. And we're going to go from left to right. So we're going to start here. And we're going to end here, kind of left to right, like we read a sentence. And basically, like I was saying a minute ago, you have new substances. New substances are formed on the right side compared to what you started with. Okay. So yeah. And we are only going to deal with just normal, ordinary chemical reactions. In that case, like if I hold out my hands, this is what you start with and this is what you end with. All of the atoms that you start with need to be kind of represented in atoms that you end with. Okay, so now the extraordinary chemical reactions, of course, would be the nuclear chemical reactions, in which you either split an atom, so you make it into two new elements, or you fuse two atoms together and make it into a heavier atom. Okay, we aren't going to be talking about those right now. So how do you know a chemical reaction has occurred? Well, sometimes you can see the change, and this, like, you can kind of see the clear at the bottom and kind of the pink at the top, okay? This actually is a type of what we call exchange reaction, where we've got two clear substances. There's a clear substance here, and then there's a clear substance here, and when you mix the two, you get this, what we call a precipitate. That's proof that a reaction has occurred. It bubbles. Okay, and I think in your first experiment we did that kind of observations lab. You guys would probably tell me, well, that looks like that's a gas coming off, so that would be new substances formed. If it releases heat, now sometimes things release heat, but no new substances are formed. Actually, a good example of that is sometimes you can just dissolve a solid, and just in the dissolving process, it's what we call exothermic. It releases heat, and that's not new substances. So not always. Okay, releasing heat, releasing light, another form of energy. It could be a sign that a chemical reaction is occurring. So yeah, like I said, you know, this visible things, you know, it could sometimes go either way, but you could for sure know that you had a chemical reaction occur if you did some sort of chemical analysis. If you knew what you started with, and then you knew what you ended with, and there was something different, okay, chemical reaction has occurred. And it's possible that a chemical reaction occurs without anything visible. You know, you can't tell it just by looking at it. Okay, so we'll take a look at these. There's a good chance we're going to get through this entire part, and so that means I count 3 assignment slides. So we'll take a quick look at this one. 7, 1. Where'd you go? this one, okay? So part of what I want to do early on is just to get you thinking about chemical reactions, okay? So, you know, answers should be in the back of the book. If they're blue, they're odd. I don't know how they answered the first one. So what is a chemical reaction? List some examples. Number 2, if you could observe atoms and molecules with your eyes, what would you look for if a chemical reaction has occurred? New substances. And then what are main indications that a chemical reaction has occurred? So just kind of put on your English hat and do your best. So, like I said, the whole chemical reaction is best summed up with a chemical equation. And I already kind of showed you kind of the left to right with like a reaction arrow between what you start with and what you end with. So chemical reactions are amazing things. Chemical reactions are amazing things, but chemical equations that describe the reactions are awesome. Okay. So we read an equation of a reaction from left to right, just like a sentence, and I'll put an R over here for reactants, and I'll put a P over here for products. Okay? Makes sense? And like the slide says, instead of the R or the P, we actually list out the chemicals that are reactants and the chemicals that are products using their chemical formulas. That's kind of like what we've been talking about. From reactants to products. So chemical equations kind of split what you start with and what you end with a reaction arrow. Now, equations can be either what we call unbalanced or balanced. Okay, an equation that summarizes a chemical reaction. I use the word unbalanced, and this textbook uses skeletal equation for something, for an equation representing a reaction, and that equation is unbalanced. So I actually want to start with the unbalanced one. So we said equations are great. You read them from left to right. You have reactants, arrow, products. Okay, and both unbalanced and balanced have that sort of thing going on. Now, both unbalanced and balanced, sometimes next to I use the word species, next to the particular formula for a reactant or product, sometimes it will say what the physical phase is. I think we've seen some of those. L will be liquid, G will be gas, S will be solid. Another thing, again, both unbalanced equation and balanced equation, is sometimes if there's something special that needs to be in place in order for that chemical reaction to occur, we say proceed from reactants to products. They'll just kind of put it concisely over the reaction arrow. I just think it's like, who needs all those words? Just put a chemical equation up there. So these are examples of what you might see next to the species, what you might see next to the reactants or the products, to kind of tell you what the physical phase is. 3 physical phases are solid, liquid, or gas, S, L, or G, respectively. And the last one, AQ, okay, and I think we've talked about this before. Anytime you see AQ, know that basically it's dissolved in water. So if you see NaCl, sometimes you'll see it like this. NaCl solid goes to form Na. Sodium is a +1 because it's 1A. And we'll write an AQ next to that, plus Cl. If you find the chlorine in sodium chloride, it's a -1, just like we talked about in the previous unit. But we'll put an AQ next to that. And I guess over the reaction arrow, we could put water if we wanted to. Water, dissolving it in water. So kind of in a nutshell then, in this scenario, we have Na pluses and Cl minuses running around. So that's what AQ means. And again, it's a nice, quick, easy way to show you that that is a substance that's dissolved in water. So what sort of things might you see over the reaction arrow, things that have to be in place in order for the reaction to proceed from reactants or products? Well, these are things like if it's endothermic, if it needs a certain amount of heat, we could put heat over the reaction arrow. If it needs a particular temperature, not too hot, not too cold, we could put that temperature over the reaction arrow. If it needs a catalyst, catalysts are great. They're actually an extra chemical that help it go faster, but they're not consumed, and they're optional. Catalysts are always optional. It's kind of fun. If it needs dark, that sort of thing. So an unbalanced equation, we were just kind of talking about chemical equations describe chemical reactions. And if it's unbalanced, it gives you what we call qualitative. The word qualitative you might get from quality. Basically kind of the general bird's eye view of what's going on with regard to the reaction. What it doesn't give you is quantitative. Of course, the word in quantitative is quantity, i.e. recipe for disaster. So if you have an unbalanced chemical equation, you can't use it as a recipe for reactants going to form products. Okay? That's reserved for a balanced equation. So these will also be due, take a quick look at these. There you are. These, I mean, again, these definitely shouldn't take you too long. You know, what is a chemical equation? Represents a chemical reaction. Give an example, and you can use your textbook. Number 5, what do these abbreviations mean? You know, you should do fine there. Okay. So unbalanced equations representing a reaction, chemical reactions, those unbalanced equations give us qualitative information. They're like a bird's eye view, quality. What are the reactants in the products? What are the physical phases? Are there any special reaction conditions? Now, a balanced chemical equation gives us quantitative information. And sometimes I think, and we'll try to kind of prove this to you as we work with balanced chemical equations, but a balanced chemical equation is truly the recipe for the reaction. It tells you, relatively speaking, how much reactants will give you how much products if you've balanced it correctly, and you will. So this is a slide I inserted, so I thought I'd kind of give you an example. For instance, I think one of the things we looked at before is you can take regular old water, liquid water, and you can run an electrical current through it, and you can break it down into hydrogen gas. Remember, hydrogen's one of those diatomic elements, so I'll put a plus, or I'll put a 2 there, and oxygen gas. Okay. I'll go ahead and let you know that this is unbalanced. Not like weird or anything, it's just unbalanced. I mean, does it say a story? Yeah, it says you start with water and you get hydrogen and oxygen. What makes it unbalanced is that if you were to, and I'll show you what I mean by this, if I go ahead and put like a wall here between my reactants and products, and if I go ahead and knock out my hydrogens and my oxygens on either side, on the reactant side, with just one H2O molecule, I have 2 hydrogens and 1 oxygen. On the product side, I have 2 hydrogens and 2 oxygens. Okay, now the hydrogens are great, they're balanced. Okay, but the oxygens are not balanced. So it's an unbalanced equation. Okay, is it wonderful? Yes. Is it balanced? No. So what we're going to do on the next few slides is talking about balancing them. Now watch this. I'm going to go ahead and write H2O liquid goes to form, that's my reaction arrow, hydrogen gas, H2 gas, plus oxygen gas, O2 gas. Now what I'm going to talk you through is, or tell you, is what I usually do is I leave a little space before each species. So I'm going to add a purple line in front of my H2O. I'm going to add a purple line in front of my H2. And I'm going to add a purple line in front of my O2. Those purple lines are important because that actually is showing you where I can put what we call a stoichiometric coefficient. I can put a big old number there to get it to balance. Well, we said my oxygens didn't work, didn't we? So let's see, to get 2 oxygens, like I have on the product side, if I put a 2 in front of my H2O, then I have 2 oxygens. So that works. But now if I put a 2 there to fix my oxygens, now it messed up my hydrogens. Now I've got 4 hydrogens to start with, and I've got 2 hydrogens to end with. I can fix that by putting another 2 in front of my H2. And now actually, if we go ahead and kind of assess the situation, hydrogens and oxygens on either side, okay, you'll see that looks like, and the other thing is, do you see this 2? It applies to the hydrogens and the oxygens. So if I have 2 H2s, that means I have what? 4 hydrogens there. I have 2 oxygens. I have 2 oxygens there. On the product side, I have 4 hydrogens, and looks like I have 2 oxygens. So it's balanced. And that's it. Some people, what we just did was to balance the unbalanced equation. So here's some other examples of balancing equations. So just kind of bare bones, notice that I have 4 P's and 2 Cl's going to form 1 P and 3 Cl's. So that's not balanced. I can fix it if I go ahead and leave the P4 as 1, if I put a 6 in front of the Cl2, and if I put a 4 in front of the PCl3. Okay, by golly, and I won't do this to all of them, I don't think, because I'll put you all to sleep. But if we go ahead and compare our P's and our Cl's, okay, it looks like I have 4 P's over here, and 6 times 2, I have 12 Cl's over there. On the product side, now sometimes students don't keep in mind that 4, it's like math, that 4 goes through everything. So that's why here on the product side, I have 4 P's, and I have 4 times 3, or 12 Cl's. See how that works? That's balanced. And so what you'll hear me say as we get running is I'll say we have a stoichiometric coefficients of 1, 6, and 4. 1, 6, and 4. Let's look at the next one. Not balanced, okay? If there's no stoichiometric coefficient, it's assumed 1. So if we go with 1s across the board there in all those boxes, goodness, I only have 1 carbon, 4 hydrogens, 2 oxygen, 1 carbon. Now this one over here on the product side, sometimes students we don't think about, we need to add these oxygens and these oxygens. So on the product side, it looks like I have, what, 3 oxygens if I go with coefficients of 1, and I have 2 hydrogens. Hydrogens aren't balanced, the oxygens aren't balanced. So I'll just go ahead and jump to the chase. If we go ahead and swap out, instead of a coefficient of 1, put a 2 in front of the O2, and put a 2 in front of the H2O, it becomes balanced. And the last one I will go ahead and show you. This is what we call an exchange reaction, and one of the things I want you to kind of think about is what we talked about in the previous unit. What I'm hoping is you recognize this guy right here as basically a cation and an anion. That's what, aluminum sulfate, okay? And if you do that, and this is what, sodium hydroxide, if you do that, this is aluminum hydroxide, and this is sodium sulfate, if you kind of keep them as units, then that actually helps your balancing. This is what we call an exchange reaction. It's kind of fun, where this cation goes with this anion, and this anion goes with this cation on the product side. So anyway, and we'll do an example coming up, but if we go ahead and go with coefficients of, this is why I kind of say it this way, if we go with coefficients of 1, this is implied 1, 1, 6, 2, and 3, 1, 6, 2, and 3, then it's balanced. And we could prove that to ourselves. Before I go on, one of the things I want to talk about is, well, two things. One is these are recipes. If I go back to the first one, if I pick on this one, it says if I have 1 part or 1 mole of P4 and 6 moles of Cl2, I'm going to form 4 moles of PCl3. It's a recipe. Reactants are like your ingredients, and the product is like what you're making. But like recipes, you can scale up. Let's just say instead of making 4 pans of brownies, you want to make 8 pans of brownies. Check this out. This is so cool. And they do this on a big scale all the time, I think. So look, if we wanted to make 8 pans of brownies, then we would have to double this, and we would have to double this. So honestly, these sets, that set of coefficients, 2, 12, and 8, are awesome too. They totally balance the phosphoruses and chlorines on either side of the reaction arrow. You can scale it up, scale it down. Okay, so the balanced chemical equation gives qualitative information, kind of a bird's eye view, a balanced equation. But a balanced equation also gives the recipe, gives you quantitative information, tells you exact quantities that react to form quantities. Okay. So a balanced chemical equation is probably, when you're looking in literature at chemical reactions, they will be balanced. But it also gives you qualitative and quantitative. So like you've seen when we kind of did some checks and did some balancing already, your goal to put that big number, what we call a stoichiometric coefficient, that big number that I kind of had like a little squiggle line before the species, your goal is to make sure on either side of the reaction arrow you have the same number of atoms of each type of element, bottom line. And I'm going to warn you, I'm going to kind of show you a way to come up with the balanced equation, and it's called trial and error. And of course, trial and error means that you're going to make some errors. And that's just kind of how it goes. You go back and forth, you use a pencil, is what I would do, to come up with a set of coefficients. It's kind of, like I said, kind of going back and forth. Now I've got some visuals to go with these. Okay, so if we make the black balls carbon atoms, and we make the white balls hydrogen atoms, and we make the red balls oxygen atoms, you can see that we don't have the same number of each type of atom of those 3 elements on either side of the reaction arrow. We just don't. Okay, it looks like our carbons are fine because we have 1 carbon, but notice our oxygens are messed up. We have 2 and 3, and our hydrogens we have 4 and 2. Okay. So we can balance that. Okay, so no, they are not balanced. Only thing that's balanced is carbon. So this is the combustion of methane. Do we get our new products formed? Yep. It's kind of a classic. During combustion, we have a hydrocarbon, which CH4 is. We end up with carbon dioxide and water. So this actually then is balanced. So notice the difference between those two equations. We've added a coefficient of 2 in front of the O2, and we added a coefficient of 2 in front of the H2O. Now just eyeballing it with the pretty pictures above, you can see we have 4 oxygens on both sides, we still have 1 carbon on both sides, and we have 4 hydrogens on both sides. So life is wonderful. So that is balanced. But just keep in mind that if you don't have a stoichiometric coefficient, it's implied 1. So we have 1 methane, 1 CH4, and we have 1 CO2. All right. Now I think I can play these. It is Monday, though. It's releasing energy, which may or may not be a chemical reaction, but it's changing physical phase from a solid to a liquid. And so we've been talking about unbalanced and balanced equations, chemical equations, and this is balanced. Okay, so I really like the animation one because it almost looks like, you know, like if you're square dancing where you swing your partner and you end up with something else. So yeah. So we'll take a look at this, and yes, this is balanced. If we go with a coefficient of 2, go with coefficients, a set of coefficients of 2, 1, and 2. That's 2 in front of the Mg, 1 in front of the O2, and 2 in front of the MgO. And again, if we start a little tally here, we could tally our Mgs and our Os, and our Mgs and our Os. Okay. Cool. This one is showing you that video. The one category of chemical reaction I talked about a minute ago, well, two. I talked about combustion reaction with the CH4 and O2 forming CO2 and H2O. I also talked about the exchange reaction where they changed partners. I just think that is so cool. And this is another one called an oxidation reaction. So we aren't going to emphasize that this semester, but just kind of throw that out there. So this whole idea, when you guys go to come up with a set of stoichiometric coefficients that give you the same number of atoms on both sides of the reaction arrow of each element, what you're doing is applying one of the many conservation laws. The big conservation laws, I think, there's the conservation of energy. Energy cannot be created or destroyed, although energy can be, and it was at the time of the Big Bang, transformed from energy into matter. That's kind of cool. And matter cannot be created or destroyed, but matter, of course, can be converted into energy, and that's what happens in our nuclear reactors. But we're tracking matter. So we have to, matter we start with needs to be represented in the matter that we end with. And we just do it by tracking atoms of the different elements. So now comes the point where I'm going to kind of show you how do you balance, how do you kind of go back and forth to come up with a set of coefficients that give you the same number of atoms of each element on both sides of the reaction arrow. There's a couple different ways. We're just going to do trial and error right now. And that's all we're going to do for this semester. But as the reason I put little squiggle marks in front of my species is to emphasize that that squiggle mark, that's the only place I can put a number. It's implied 1 if I don't put a number. I can put a 1 if I want. But that's the only thing I can do. I can't change the subscripts, because if you change the subscripts, then you're changing the chemistry. You're changing the reactants and the products. The subscripts go with the compounds, okay? Yeah. So that big, I call it the big number to the, I get my left and rights mixed up. The big number to the left of the species, that's the number you can change. It's called a stoichiometric coefficient. Stoichiometric coefficient. Sometimes I call it STOICH, COEF, COEFF. So when you put a number other than 1, the big number stoichiometric coefficient in front of the species, just make sure that you know it, like we were doing a minute ago, that it applies to the whole species. It applies to the whole species, all of the different atoms of different elements in that species. Okay, so let's go ahead and balance this. So I'm going to kind of show you, actually my daughter, when she took chemistry, we have 2 daughters, and one of them said this is what her teacher showed her to do. So I was like, that's pretty cool. So I'll put my little squiggly marks there in front of everything. I'll draw my brick wall between reactants and products, and then I'll go ahead and start my tally. I have Fe, that's iron, I have H, hydrogens, and I have O's, oxygens, on both sides of the reaction arrow. Fe, H, O. And then what I do is go ahead and write what I have if I just go with coefficients of 1. So I go with coefficients of 1 across the board. I have 1 Fe, I have 2 hydrogens, I have 1 oxygen on the reactant side. I have 3 irons, 2 hydrogens, and 4 oxygens on the other side. And then I get a cup of coffee because, yeah. So my hydrogens are good to go, but actually they're good now, but they may, through kind of balancing this, be what we say temporarily messed up. My oxygens are not right, and my irons are not right. Now, I have a slide to tell you this, but I'm going to put a little asterisk next to my Fe. Okay, that little green asterisk up there, I'm going to leave that for last, because it is what we call, you see where it looks like it's low-hanging fruit. It's going to be pretty easy because it's by itself. Okay, so I can either focus on my hydrogens or my oxygens. So it looks like I better focus on my oxygens. So it looks like if I have 4 over here, I can get 4 over on the reactant side if I put a big old 4 here next to my H2O. So if I put a 4 right there, then I have to update my tally. So my iron's the same, but now if I put a 4 in front of H2O, I have what, 8 hydrogens now. So I'm going to take that 2 and I'm going to change it to an 8. And I'm going to take that 1 for the oxygen, and I'm going to change it to a 4. I have to update. So now my oxygens for now look great. I'll put a little check mark there saying they look great. But now my hydrogens are mixed up. So now I'm going to actually turn to the product side. This is why you kind of go back and forth on either side of the reaction arrow. So I only have 2 on the product side, but I need 8. So if I put a 4 in front of that H2, that should do it. So here we go, 4 in front of the H2. Okay, and so I'm going to update my H's, and I went from 2 to now I have 8. I'm going to put little check marks next to my hydrogens. Now the only thing that's not right are irons, and I can see that I need to put I have 3 on the product side. I can get 3 on the reactant side if I put a 3 here. And now I update my irons, and now I got 3 and 3, so I'm cool. So the set of coefficients would be 3, 4, 1, and 4. Looks pretty good. Okay. So 3, 4, 1, and 4 are kind of, it's the recipe. It's how they react on a relative mole basis, or relative atom and molecule basis, and formula unit basis. They're pretty cool. Some people really like balancing equations. If you get stuck for balancing equation, and maybe I'll put it out there on Twitter, they're actually there are online solvers for you. You can put in the reactants and the products, and they'll spit you back a balanced equation. Kind of cheating. But, so this is the tally that we did. I don't think you need anything here, right? Okay. So let's do another one. Now this actually looks like the one that I gave as an example before. Oh, you know what? If you need examples for equations, you can just go to your notes. For your homework, you can just go to your notes if you wanted to. Okay, so in this one, I'm going to go ahead and put my squiggly marks. Squiggly mark in front of the Al2SO4 quantity 3. Squiggly line in front of the NaOH. Squiggly line in front of the AlOH quantity 3. Squiggly line in front of the Na2SO4. Now when I balance this, I usually, like I told you before, I think of it as my aluminums. I think of it, actually I should say, as my SO4. I'm going to leave it as an SO4 unit. Sodium hydroxide, I'm going to leave my OH as a unit. aluminum hydroxide. Of course, OH is going to be a unit. Sodium sulfate, SO4 is going to be a unit. So with that in mind, we'll go ahead and draw our brick wall between reactants and products. Let's see. The thing I need to balance, what I got are aluminums. I'm going to go ahead and, because we talked about it, I'm going to go ahead and put aluminum plus 3. It's kind of optional. We know it's 3 because it's 3A. I'm going to put SO4 2 minus because we talked about it. Again, those are optional. I'm going to put Na plus 1, and I'm going to put OH minus 1. And I'm going to do the same thing over on the other side. So it's aluminum plus 3, SO4, 2 minus, sodium plus, and OH minus or minus 1. So with just coefficients of 1, I got 2 aluminums, I've got 3 sulfates, I've got 1 sodium and 1 hydroxide. On the product side, I got 1 aluminum, I got 1 sulfate, I got 2 sodiums, and I got 3 hydroxides. So remember I put an asterisk next to the Fe before? So I don't think I have anything necessarily to put asterisks next to this time. But I'm probably going to focus on what I think is maybe the messiest. So for instance, I have 3 SO4 groups over there to start with, and I only have 1 SO4 group over here. So I know I gotta increase my quantity on the product side. So I think maybe I'll start there this time. So if I need 4, if I put a 4, I'll put a number 4 right here. I'll kind of squeeze it in. If I put a 4 there, then update my quantities. Now when I put a 4 there, it looks like I increased my sodiums from 2. Now I need to update that to what, 8? And when I put a 4 there, that increased my sulfates from 1 to 4. Oh, see? I didn't want to do that. I wanted 3, didn't I? Okay. Let me change that to a 3. That's better. So now, see, that's why I need a pencil. So now my sodiums are not 2, they're what, 6? And now my sulfates are not 1, they are 3. That's better. So now my sulfates are fixed. Awesome. Well, let's go ahead and fix our hydroxides while we're at it. Notice that we have 3 hydroxide or OH minuses over here. To get 3 over on the reactant side, I can do that if I put a 3 right here in front of the NaOH. Let's go ahead and update. So now my sodiums aren't 1, now my sodiums are 3, and my hydroxides aren't 1, they are 3. So let's put a check next to things for now that are right. I fixed my sulfates and I fixed my hydroxides. Oh, goodness gracious. It's going to get messy. So it looks like my aluminums aren't right. So I have 2 aluminums, okay? So to start with, so to get 2 aluminums to end with, here we go. This is back and forth. I'm going to squeeze in a number 2 here. And now I update everything. So that gave me, instead of 1 aluminum, now I have 2. And for hydroxides, I have 2 times 3. I end up with 6 hydroxides. I'm going to update that to 6. So I fixed my aluminums, but I messed up my hydroxides. Oh my gosh. So let's go ahead and fix our hydroxides again. Now I have too many hydroxides over here. I have 6. So notice that to get 6 hydroxides on the reactant side, if I'm going to cross out that 3, it's looking messy, you can erase it, and I'm going to put a 6. And I'm going to update my sodiums and my hydroxides. So now if I update my sodiums, it's not 3, it's 6, If I update my hydroxides, it's not 3, it's 6. So, I don't know. It's kind of like playing one of those games where things just kind of finally fall into place. So if I go with a coefficient of 1, 6, 2, and 3, that works. Yay! Okay. Did I have to go back and forth a few times? Yep. Notice that this is the balance if you left them, this is the balance we did. Okay, they're equal. But if you broke it down into, instead of sulfate, if you had sulfur and oxygen, instead of hydroxide, if you had oxygen and hydrogen, it would be the same, it would also balance.
I have a question.
Uh-huh.
Do we have to do it by compounds like SO4 and stuff, or can we just do it like just by individual?
You can just do it by individual. It'll still work. Yeah. Yep. This one is, remember I put an asterisk next to the FE? This is that. This is talking about that. So you just like, if something looks, I called it low-hanging fruit. If something looks kind of easy, if I'm last minute throw a coefficient there, just leave it till the end. All right, let's do one more example. Now the problem with this one is that, and we kind of talked about this a little bit ago, anytime you have a combustion problem, this isn't CH4 combusting, this is C4H10 combusting, combining with oxygen, again to form carbon dioxide and water. The problem is that we have oxygen in 2 places on the product side. So we're going to have to take that into account. So here's my brick wall, here's my tally for carbon, hydrogen, and oxygen. Here's my tally for carbon, hydrogen, and oxygen. So to start out with, looks like I got 4 carbons, 10 hydrogens, 2 oxygens to start with on the reactant side. I have, on the product side, I have 1 carbon, 2 hydrogens. Now oxygens are 3. See, I have 2 plus 1. I could put a little asterisk next to my O2, because that's kind of like my FE. It's like, I'm going to save that till last. What I usually do is go for my carbons first. So let me put little squiggly marks here. Where the squiggly marks are, I can go ahead and put stoichiometric coefficients instead of 1. So to get 4 carbons on the product side, if I put a 4 in front of the CO2, that will give me 4 carbons. And I need to update my oxygens. Now oxygens, I have 8 plus 1. I have 9 oxygens instead of 3. Let's go ahead and fix our hydrogens. I have 10 hydrogens in the reactant side, so I need 10 hydrogens on the product side. I can get that if I put a coefficient of 5 in front of the H2O, because that will give me 5 times 2 is 10. So if I update my hydrogens, now I've got 10 hydrogens over here. 5 times 1 for the oxygen is 5. So I have 5 oxygens there, but don't forget about, goodness, the other 8 oxygens. So 5 plus 8, I get 13. So I need to update my 9 to a 13. So if I were going to do little check marks, you know, I have got the carbons are done, the hydrogens are done, and the oxygens are not done. So I have 13 on the product side, but I only have 2 on the reactant side. We have a problem of the oxygens come in pairs, but I need an odd number, okay? So you can do one of 2 things, and I'll show you what I usually do. I think of O2, and we'll talk about this on Wednesday, as you can actually have a half of an O2 if you think of it in terms of a mole. Okay, a mole is 6.022 times 10 to the 23rd molecules. You can have a half of a mole. So actually, if I go with a 1/2 here, okay, I can kind of fix my evens, oddsies things. So let's see. 13 is, let's see, 6 times, how do I say it? 6 and 1/2 O2s. Does that make sense? Okay. 6 and 1/2 O2s. 6 and 1/2 O2s, that's the same thing as 13 halves. Honestly, the way I probably would go by working this is I can put a 13 halves there, and that's fine. If I go with 13 halves there, do you guys buy that? That actually gives me, I can update my oxygens. Instead of 2, I will have 13. So that's one way to balance it. Okay. That is totally one way to balance it. Remember I said you could scale these things up, like make double brownies or something like that? Okay. So if we wanted to get rid of that fraction 13 halves, we could scale it up by a factor of 2. Just multiply all coefficients by 2, and that gets rid of it. So actually, if we did that, we'd end up with a coefficient of 2 in front of the C4H10, a coefficient of 13 in front of the O2, 8 in front of the CO2, and 10 in front of the H2O. So both of those are perfectly valid ways of showing a balanced equation for this reaction. Totally, totally fine. So they both work out. So like I said, fractional moles, like that 13 halves, are fine. As long as instead of molecules, because you can't have a half a molecule of, you can't have a half of an O2 molecule, but you can have a half of a mole. All right. So I do have an important something to add here. That first problem that you're asked to do, we're not quite done, Kay. You can come in and listen to chemistry. That first one that you're asked to do, I want to give you the chemical reaction. So it looks like, give you the unbalanced one. You guys can balance it. Should be here. I guess I'm going to have to tweet it. How did it slip somewhere else? Okay. Well, when you look at these, you'll see what I mean. I'll make 6, is it 6? I'll make 48 optional, because it was 48. 48's worth extra credit. You guys are great with extra credit. 48 is worth extra credit. That's the only one. So extra credit. How's that? Okay? Got a lot of homework for Monday, or for Wednesday.
And I apologize.